Welcome to the next installment of Math 1111 General Skill number 6, in which we are talking about solving systems of linear equations. And this video, we're going to focus on solving systems of linear equations by using elimination. Some textbooks call this using addition. Some textbooks call it using linear combinations, but in our textbook, we are going to call it elimination. So let's look at how do we do this. This is a tool that we can use in addition to substitution, and it's especially helpful when you have a system where there are multiple variables that have coefficients other than 1. So the whole idea of elimination is we want to eliminate in the entire system all the x's or all the y's. So I can focus on my attention on eliminating the set of x's here, or I can eliminate the set of y's. Sometimes there's a better option than others, but often it doesn't really matter. The idea of eliminating a variable comes into play when we manipulate one or both of our equations so that they will have the same coefficient on the variable we're trying to eliminate, but different signs. So in other words, I want a set of variables like positive 5x and negative 5x, or positive 12x and negative 12x, or positive 30y and negative 30y. The whole idea there is we want to be able to add them together and eliminate them completely. So in this system, you could definitely eliminate the x's, and by if we wanted to do that, we would look at the relationship between the 2 and the 4, and if one is a factor of the other, we would multiply the one that's a factor by what we would need to multiply it by to achieve the product multiple that is the coefficient of the other variable here. So in this case, if I multiply this 2x by 2, I would get a 4. I would get a 4x actually, right? But we really want to make this a negative 4x so that when I add it together with this 4x, it will be eliminated. So I can eliminate x by multiplying the entire top equation by negative 2. And like the thought bubble says here, that would result in a negative 4x on the top, which when I add it to the positive 4x would totally eliminate the x's. So that's one method or one way we could eliminate a set of variables in this system. Another way is we could focus on the y values. Now this one is a little bit different because 4 is not a factor of 5 and 5 is not a factor of 4. So we would have to manipulate both equations in order to make the y's disappear. So we would actually take the coefficient of one of the y's and multiply it by the other, and we would treat these as factors of a common multiple. And in this case, if I multiplied a negative 4 by 5, I would get a negative 20y. And if I multiply a negative 5 by 4, I'd get a negative 20y as well. So the idea, though, is we wanted one to be positive and one to be negative. So one of these would need to be multiplied by a negative version of the other coefficient. And it doesn't matter which one. So I could multiply this top equation all by positive 5 to get a negative 20y. And if I got a negative 20y here, I would want a positive 20y here. So I would multiply this bottom equation by negative 4. Okay, and vice versa, you could have used a negative on the top and a positive on the bottom, but the whole idea is we want to have a result where the coefficients are the same value but opposite signs. So let's go back and use the more efficient option, because the first option we only had to multiply one of our equations all the way through. So let's go back and use the more efficient, I won't say lazy, I'll say efficient, right, method of solving the system. So let's go ahead and multiply the top equation, the entire equation, all through by -2. And when I do that, I need to make sure that -2 goes all the way across. So I would have a result of -4x plus 8y is equal to -26. Now I'm going to leave that bottom equation alone because notice these line up with the same term, right, with opposite signs. And so I can go ahead and add them together. And when I add them together, those x's just cancel each other out. The -4x plus 4x is 0x, and we just don't even need the 0 there. So we would have a result of 3y is equal to -18, which is super simple to solve because we would just divide both sides of that equation by 3 and get a result of y is equal to -6. Now, like when we use substitution, we are not finished when we get our first result because we want a solution to the system, which is really a coordinate of a point. So we need the x value as well. And for that, we're going to go ahead and substitute that y value back into one of the equations. And it doesn't matter which one. You can sub it in the top or the bottom. But when we do that, we will be able to solve for the x value. So we would have 4x minus 5 times -6 is equal to 8. And so that would become 4x is equal to -22. And x is equal to -22 divided by 4, which simplifies to -11/2. So we think that our solution is the coordinate or the ordered pair -11/2, comma -6. And like we did before, we would want to just verify that. So check your solution by substituting it into both of the original equations. So let's go ahead and sub it into the first equation. Oh, and some of you are groaning because you're putting in a fraction. Okay, yeah, but look at what happens here. If I take this 2 and I multiply it by -11/2, these 2's will cancel out because 1 is on the top and 1 is on the bottom. When I multiply this 2 by -11/2, I just get a result of -11. And -11 plus 24 is indeed equal to 13. So 13 is equal to 13. All right, and then we would try in the second equation. Same thing, 4 times -11/2 minus 5 times -6. We want to make sure that that is equal to 8. And while these don't cancel out, 4 divided by 2 is the same as just 2. So this is 2 times -11, also known as -22 plus 30. And -22 plus 30 is indeed 8, which is equal to 8. So we are good to go here. So it's your turn to try. Your turn to try with this system of equations. Now notice that you are going to need to multiply both of the equations by something to get one set of variables to cancel out. You go ahead and try, pause the video, and we'll go over it in just a second. Okay, now welcome back, and let's go through this system of equations, solving it. I chose using the x values to eliminate, and I could have just as easily done the y's. If there's not really an advantage, I tend to use the variables in the front, just because to me they're easier to work with. And in order to eliminate these x variables, I'm going to multiply the top equation all the way through by -5 and the bottom equation all the way through by +2. When I do that, I end up with -10x minus 15y is equal to +80. Okay, for the top equation. And the bottom equation becomes positive 10x minus 20y is equal to 60. Notice I have two terms with x's lined up right on top of each other, and one is positive while the other is negative. So that means I'm going to go ahead and add them together, which is going to eliminate them. And I am going to be left with a very simple equation of negative 35y is equal to 140. Dividing out the negative 35 will give me y is equal to negative 4. Now I'm going to take that negative 4 and substitute it back into one of those equations. And like I said, it doesn't matter which one. I chose the top one this time. So if I plug in that negative 4 where I see y, I'd be left with the equation 2x plus 3 times negative 4 is equal to negative 16. So 2x minus 12 is equal to negative 16, or 2x is equal to negative 4. That will give me an x is equal to negative 2. So I think my solution is negative 2, negative 4. I would, of course, go ahead and verify that by substituting that ordered pair in and making sure that the left side does equal the right side in both of my equations. Once I do that, I can be confident that my answer is correct. Okay, next time we're going to talk about how do we recognize when a system of equations does not have a single solution. It could have no solution or infinite solutions, and that's what we'll pick up next time. See you then.